La la la. Myopia, 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 myopia. Near distance we can see her. Far distance we can see her. Myopia, myopia, myopia. For that correction we are using concave lens, concave lens, concave lens, concave lens. Myopia, 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 myopia. Near distance we can see her. Far distance we can see her. Myopia, myopia, myopia. For that correction we are using. Bro, what bro? For that correction we are using concave lens, concave lens, concave lens, concave lens. Hypermetropia, 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 hypermetropia. Far a distance we can see, near distance we can see. Hypermetropia, 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 hypermetropia. For that correction we are using convex lens, convex lens, convex lens. Hypermetropia, convex lens, hypermetropia, convex lens, hypermetropia, convex lens. The Cartesian sign convention, the Cartesian sign convention, all the distance measured from the pole. Distance positive along the incident phase. Distance negative opposite to incident phase. Distance positive above the principal axis. Distance negative below the principal axis. New Cartesian sign convention. New Cartesian sign all the distance measure from the pole. Distance are positive along the incident trace. Distance are negative opposite to instant trace. Distance are positive above the principal axis. Distance are negative below the principal axis. Say with me, learn with me, sing with me. Say with me, learn with me, sing with me. Dispersion, dispersion. Splitting the white light into 7 colors is known as dispersion. Dispersion. Refraction of light takes place in atmosphere is known as atmospheric refraction. Atmospheric refraction. Atmospheric refraction. Atmospheric refraction. The process of re-emission of light in all directions with a different intensity is called scattering of light. Scattering of light. Scattering of light. Scattering of light. Dispersion. 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 Splitting the white light into 7 colors is known as dispersion. 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 Refraction of light in the atmosphere is known as atmospheric refraction. The process of re-emission of light in all directions with a different intensity is known as scattering of light. Scattering of light. Dispersion. Dispersion. Say with me, learn with me, sing with me. Dispersion. Myopia, myopia, myopia. Myopia, myopia, myopia. Near distance we can see a far distance we can see a myopia, myopia, myopia. For that correction, we are using concave lens, concave lens, concave lens, concave lens. Hypermetropia, 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 hypermetropia. For that correction, we are using convex lens, convex lens, convex lens. Hypermetropia, convex lens. So like that, so we are discussing about hypermetropia, myopia. So with the help of songs we discussed it till now. Now we are ready to discuss, ready to learn about electric current. Electric current, electric current, electric current. Electric current is nothing but electric current is nothing but electric current is nothing but okay, so the rate of flow of charge, the rate of flow of charge, rate of flow of charge. Okay, so we are going to discuss about electric current. So we are going to discuss about electric current. So now we will discuss about electric current. Electric current, electric current, electric current. CBSE grade 10 physics, CBSE grade 10 physics, CBSE grade 10 physics, physics, physics. So electric current is nothing but I equal to Q by T. I equal to Q by T. I equal to Q by T. So I'm considering I equal to Q by T. So now I'm considering I equal to Q by T. Q by T is nothing but SI unit of current is ampere. SI unit of current is ampere. SI unit of charge is coulomb. SI unit of charge is SI unit of charge is coulomb. SI unit of current is SI unit of current is ampere. SI unit of charge is coulomb. SI unit of current is ampere. SI unit of charge is coulomb. SI unit of time is second. SI unit of time is second. So now you are considering here. So this is the coulomb I am considering. Okay. So here I am considering SI unit of charge is coulomb. SI unit of charge is coulomb. SI unit of time is second. SI unit of time is second. Here I am considering. So here I equal to Q, I equal to SI unit of current is ampere, SI unit of current is ampere, SI unit of charge is coulomb, SI unit of charge is coulomb, SI unit of time is second. So current is defined as the rate of flow of charge, the rate of flow of charge, the rate of flow of charge, a flow of charge through unit cross section area per second. Flow of charge through unit cross section area per second is called electric current. Flow of charge through unit cross section area per second is called electric current. So if you are taking here, if you are considering here, okay, so this is the so I'm considering here so conductor I'm considering, this is a conductor, this is the conductor I'm considering. So current will pass through the conductor, current will pass through the conductor, current will pass through the conductor, current will pass through the conductor. So the flow of charge through unit cross section area, flow of charge through unit cross section area I'm considering. Flow of charge through unit cross section area per second is called electric current. SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. Okay. So I equal to Q by T. 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 SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. So 1 ampere is defined as 1 coulomb of charge flowing. So 1 coulomb of charge flowing through unit cross section area per second. 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second. 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second is called 1 ampere. So 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second is called 1 ampere. 1 ampere equal to 1 coulomb of charge flowing through unit cross section area per second. Okay, so if they ask to define SI unit of charge, if they ask you to define SI unit of charge is 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second. 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second is called electric current. So 1 ampere equal to 1 coulomb per second, 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 1 coulomb per second. So here quantization of charge is nothing but inside of the conductor, electrons will not flow 1, 2 like this. So electrons will not flow 1 electron, 2 electron, 3 electrons will not flow. So there are number of electrons will flow, number of positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. Like that, there are number of bunch of electrons will flow. So number of electrons will flow. That's why it is called quantization of charge. Quantization of charge is nothing but so number of electrons will pass through the conductor, number of electrons will pass through the conductor, number of electrons will pass through the conductor. So I equal to q by t if you are taking, right. So q is the quantization of charge, so that is number of electrons will pass. So if you are taking the charge, we can say number of charges, either positive charge or negative charge, positive charge or negative charge. So because of the charge, so because of charge movement only, the so charges are moving inside of the conductor. So charges are moving inside of the conductor, then only we can say current is passing, then only we can say current is passing inside of the conductor. So charges, so like if you are taking electrons 1 or 2, it won't flow. Like number of integral multiple. So number of electrons, number of charges will move. So positive charges, negative charge. There are two types of charges are there. There are two types of charges. So charges are two types. So positive charge and negative charge. So positive charges and negative charge. Positive charge is nothing but positive charge. Positive charge, if you are considering, positive charge is the proton, negative charge is the electron. Positive charge is the proton, negative charge is the electron. Positive charge is the proton, negative charge is the electron. Positive charge is the proton, negative charge is the electron. So here I am considering, so positive will repel, positive will repel, positive will repel, negative will repel, negative will repel. So positive negative, so will attract. So positive negative will attract at the same time. So negative positive also will attract. Negative positive also will attract. Charge is a property of the matter. Charge is a property of the matter which influence the presence of other charges. So charges, if you are taking, so electrons will move from negative terminal to positive terminal. Electrons will move from negative terminal to positive terminal. So positive charges will move from negative terminal to positive terminal. Now positive charges will move from positive terminal to negative terminal. Whereas electrons will move from negative terminal to positive terminal. Actually, before finding the proton, neutron, electron, so proton, electron, all these things. So before scientists were given the definition, so charges will move from positive terminal to negative terminal, positive terminal to negative terminal. Current, if you are taking current direction, positive terminal to negative terminal. After identifying, because of the electrons movement only current will pass inside of the conductor. Because of the electrons movement only current will pass in the current will pass in the conductor. So that's why we are considering positive charges direction will be taking positive terminal to negative terminal. Electron direction will be taken negative terminal to positive terminal. So here I am considering charges are two types. So positive charges, negative charge. Positive charges, positive charge and negative charge. So positive charge repel, negative charge will repel. Positive negative will attract, negative positive will attract. Okay? Those are the two types of charges. Those are the two types of charges we are discussing. Next one, if you are considering, next one if you are taking, okay, so I'm considering here, so I equal to q by t, I equal to, so 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area. 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second. So as I said, charges are two types, positive charge and negative charge. Positive charge and negative charge, as I said, positive charge and negative charge. Okay, so here I equal to q by t, as I said, I equal to q by t. Q is nothing but integral multiple of Ne. So plus or minus. Why we are taking plus or minus? Why we are taking plus or minus? Because why we are taking plus or minus? Because there are positive charges are there, negative charges are there. Positive charges are negative charges, both are there. Positive charges and negative charges, both are there. Positive charges are negative charges, both are there. That's why we are taking plus or minus. Integral multiple. Charges will move inside of the conductor in the form of integral multiple. Only one electron it will pass, we can't say. Only two electrons will pass, we can't say. So number of electrons, a bunch of electrons will pass in the inside of the conductor, then we can say current is passing inside of the conductor. Current is passing inside of the conductor. So Q equal to plus or minus Ne. Q equal to plus or minus Ne. Q equal to plus or minus Ne. I am considering Q equal to plus or minus Ne. Q equal to plus or minus I am considering Q equal to plus or minus Ne. Q equal to plus or minus Ne. So in one electron, so on one electron, 1.6 into 10 power minus 19 coulomb. So on one electron, how much charge is present? So on one electron, 1.6 into 10 power minus 19 coulomb. So in one coulomb, how many electrons are present? Yeah, so everybody, hi, welcome to the class. So welcome to the student, the brand. Okay, so in 1 coulomb, how many electrons are present? In 1 coulomb, how many electrons are present? In 1 coulomb, how many electrons are present? So that is the reason. So now you are considering here 1 coulomb if you are taking, 1 coulomb if you are considering, 1 coulomb equal to 1 by 1.6 into 10 power minus 19. Okay, so if you are taking in that way, if you are considering in that way, if you are considering that way, so you can consider here, if you are considering here, okay, so take like this. I am taking 1.6 into 10 power minus 19 coulomb, 1.6 into 10 power minus 19 coulomb, 1.6 into 10 power minus 19 coulomb I am considering. Okay, so if you are taking 1 by 1.6 into 10 by 10, if you are taking into 10 power 19, into 10 power 19. So 10 by, so 16 if you are taking 10 power 19, 10 power 19. So if you do 10 by 16, 10 by 16 if you do, you'll get it 10 by 16 if you do it, 10 by 16 if you do it. So if you're solving 10 by 16, so into 10 power 19, 10 power 19, if you do this one, you will get 0.625 into 10 power 19. So still if you are removing one value, 6.25 into 10 power 18. So electrons in 1 coulomb, 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 6.25 into 10 power 18 electrons. In 1 coulomb, 6.25 into 10 power 18 electrons. In 1 coulomb, so 6.25 into 10 power 18 electrons are present. In 1 coulomb, 6.25 into 10 power 18 electrons are present. So once again, I equal to Q by T. I equal to Q by T. So I equal to Q by T I am considering. I equal to Q by T. So Q is the charge. So T is the time, I equal to Q by T, I is the current, Q is the charge, T is the time. So I equal to Q by T. So Q is the charge, I is the current. SI unit of current is, ampere, SI unit of current is ampere, SI unit of charge is coulomb, SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second, SI unit of time is second. So I equal to Q by T. So the rate of flow of charge, the rate of flow of charge is called electric current. Rate of flow of charge is called electric current. The flow of charge through unit cross section area, per second. The flow of charge through unit cross section area per second is called electric current. The flow of charge through unit cross section area per second is called electric current. The flow of charge through unit cross section area per second is called electric current. SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. I equal to Q by T. So 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. So 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area. 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second is called electric current. So electrons will flow integral multiple. Electrons will flow inside of the conductor. Integral multiple it will flow. Okay. So here I am considering. So plus or minus any I am taking. Why plus or minus any? Because why plus or minus any in the sense? So positive charges will be there, negative charges will be there. Positive charges will be there, at the same time negative charges will be there. That's why we are taking plus or minus Ne. Plus or minus Q equal to plus or minus Ne. So integral multiple of charges will move inside of the conductor. Integral multiple. So Q equal to plus or minus Ne. So I am considering here on one electron how much charge is present. On one electron 1.6 into 10 power minus 19 coulomb. On one electron 1.6 into 10 power minus 19 coulomb. In 1 coulomb how many electrons are present? In 1 coulomb how many electrons are present? 1 coulomb equal to 1 by 1.6 into 10 power minus 19. So 1 by 1.6 into, if you are taking here, in 1 coulomb 1 by 1.6 into 10 power minus 19. So here if this 10 power 19 we are taking up, okay. So here I am considering 1 by 1.6 into 10 by 10. 1 by 1.6 into 10 by 10 I'm considering. 10 by 10. Okay, so 10 power 19 it will be there. So 10 by 16 into 10 power 19. So 10 by 16 is the value. So 10 by 16 is 0.625. 10 by 16 is the value 0.625. 0.625 into 10 power 19. So if you do it, so if you are taking one value this side, so in one coulomb, 6.25 into, in 1 coulomb 6.25 into 10 power 18 electrons are present. So in 1 coulomb 6.25 into 10 power 18 electrons are present. So very important, very important. Most important, definitely one mark question will come. 1 mark question, so I equal to Q by T, 1 mark question will come, definitely this type of question. And so you have to remember this value, and on 1 electron 1.6 into 10 power 19 I said, right? This value compulsory you have to remember, because in exam they won't give in exam, so we have to remember that value. And this value 6.25 into 10 power 18 electrons, so in 1 coulomb 6.25 into 10 power 18 electrons, that also we have to remember, because so that is very important, very important exam point of view, in MC, especially in MCQ point of view, MCQ's point of view, these 2 points are very important. MCQ's point of view, these 2 points are very important, very important. So very important. Okay, so make sure that you are preparing this one, you are preparing these 2 points, so prepare well. Okay, so practice 2-3, so 2-3 times. If you practice that value, you can remember. So in 1 coulomb, on 1 electron 1.6 into 10 power minus 19 coulomb. So in 1 coulomb, how many electrons are present? In 1 coulomb, how many electrons are present? In 1 coulomb, so 6.25 into 10 power 18 electrons. Okay, so these 2 points are very important. Make sure that you are learning these 2 points. Clear? So next one, we are going to discuss about one more, electrical appliances. Electrical appliances will discuss. Okay, so electrical appliances. What are the electrical appliances? So what are those? We'll see now. So there are positive terminal, negative terminal, positive terminal, negative terminal. Okay, so positive terminal, negative terminal. So that is cell. So if you are taking 2 or more cells connected together, connected together, that is battery. So one I am taking the cell, one I am considering the cell. Cell if you are considering, first one is so this is the cell, 1 point, so positive terminal, negative terminal cell. And coming to the second one is the battery. Battery I am taking 2 or more cells together, positive, negative. Battery I am considering, battery. Okay, so third one is switch. I am considering switch you are taking. So this is the switch. This is the open switch. Okay, so this is about open switch. And coming to this one, closed switch. Okay, so this is the closed switch. If dot is there, closed switch. Okay, so this is a cell, battery, open switch and closed switch, So they am taking here this the closed switch. And next one, fifth one is resistor. I am taking resistor is this one, resistor. This is a resistor. And sixth one is rheostat. Next one is we are talking about rheostat. Rheostat is like this. Either we can take like this, we can consider like this, So observe here, this is the rheostat. Okay, so cell, battery, open switch, closed switch, resistor, rheostat. Next one, we are going to the next one, ammeter. Seventh one is ammeter, positive terminal, negative terminal. So eighth one is voltmeter, positive terminal, negative terminal. Next one is wire joining. This is a wire joining. And the 10th one is wire crossing. And the 11th one is bulb. So So bulb I'm considering, this is a bulb. Okay. So this is about electrical appliances, once again you can check once again you can check here. Okay. So what are the points are there? What are points are there? So first one you can see, this is a cell, battery, open switch, closed switch, resistor, rheostat, resistor and rheostat, and here so ammeter, voltmeter, wire joining, wire crossing, and a bulb. Okay, so these are the electrical appliances. These are the electrical appliances. So whatever we are considering, all these points are electrical appliances. So now we will discuss about electrical circuit. Will discuss electrical circuit. So a continuous and closed path of an electric current. A continuous and closed path of an electric current is nothing but electric circuit. A continuous and closed path of an electric current. Okay, so now we will see. So we'll discuss about it. So I'm considering now. So ammeter, voltmeter. So here you can observe. So electric circuit is nothing but a continuous and closed path of an electric current. A continuous and closed path of an electric current. A continuous and closed path of an electric current is nothing but electric circuit. Electric circuit. Okay, so electric circuit I am talking. So here this is a battery. This is a battery I'm taking here, positive terminal, negative terminal. So switch, so closure switch, and here so I'm taking the bulb. Here. Okay, so that I'm connecting. So I'm connecting positive terminal, negative terminal. Current is passing like this. Yes or no? Current is passing like this. So you can observe here. You can observe one point. Okay, so bulb is glowing, glowing bulb. So here you can observe, if the current is passing inside of the conductor, okay, so what is the current direction we will consider? Current direction is positive terminal to negative terminal we are concerned. Positive terminal to negative terminal. So like this we are concerned. There are two types of currents are there. So conventional current, and second one is electric current, conventional current and electric current. So what is a conventional current? Conventional current is nothing but, so actually the flow of positive charges will be considered as a conventional current. As I said before, finding electron, proton, scientists were given the statement, the flow of positive charges, the direction of flow of positive charges will be considered direction of the current. So direction of the current. Okay. So we are taking the current direction from positive terminal to negative terminal, from positive terminal to negative terminal. Current direction will be considered. We are considering. Okay. So the flow of positive charges will be considered from positive terminal to negative terminal, from positive terminal to negative terminal. So that is a conventional current. What about electric current? The flow of electrons. The electrons direction will be considered like this. The electron direction, here positive charges. So conventional current will be taken flow of positive charges. Electric current will be taken flow of electrons. Positive charges will move from positive terminal to negative terminal. So electrons will move from negative terminal to positive terminal. Here one point. Okay, so positive charges will move from high potential to low potential. Positive charges will move from Positive charges will move from high potential to low potential, whereas negative charges, electrons will move from low potential to high potential. Very, 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 very important. Very, very important. Very, very important. Positive charges will move from positive terminal to negative terminal. Negative charges, electrons will move from negative terminal to positive terminal. Negative terminal to positive terminal. Negative terminal to positive terminal. Positive charges are nothing but protons. So positive charges will be taken the direction of the conventional current here. Conventional current direction will be taken. Flow of positive charges direction. Positive terminal, negative terminal. So electric current. So electric current is nothing but negative terminal to positive terminal. Negative terminal to positive terminal. Clear? Yes or no? And one more point is positive charges will move from high potential to low potential. Positive charges will move from high potential to low potential, whereas negative charges will move from low potential to high potential. Positive charges will move from high potential to low potential. Negative charges will move from low potential to high potential. Very, very important. Conventional current and electric current. Conventional current and electric current. So I hope it is very clear to you all. Next one. So electric current, conventional current and electric current. Next one we'll discuss about a potential difference. So we'll discuss about potential difference. So now we will see potential difference is nothing but when the current is passing inside of the conductor. So okay, so positive charges. So potential difference and electrical potential, two terms are there. Potential difference and electrical potential, two terms are there. Potential difference and electrical potential. Potential difference and electrical potential. Potential difference is nothing but potential difference. Okay. Potential difference is nothing but work done to bring unit positive charge. Work done to bring unit positive charge from one point to another point within the conductor. Work done to bring unit positive charge. Work done to bring unit positive charge from one point to another point. Work done to bring unit positive charge from one point to another point within the conductor. If you are taking this a conductor, so this is a point A. I am considering this is a point B. So positive charge. So we are doing work. Okay. So we are doing some work. To bring unit positive charge from one point to another point within the conductor. We are doing some work to bring unit positive charge from one point to another point. Within the conductor. Work done to bring unit positive charge. From one point to another point within the conductor. Work done to bring unit positive charge from one point to another point within the conductor. Within the conductor is called potential difference. So V equal to W by Q. So V I am considering V equal to W by Q. So SI unit of potential difference is volt. SI unit of work is joule. SI unit of charge is coulomb. So 1 volt equal to 1 joule. 1 joule of work is done. So if you are asking to define 1 volt, so 1 volt, define 1 volt. 1 joule of work is done to bring. So 1 coulomb, 1 volt is defined as 1 joule of work is done to bring 1 coulomb of charge from one point to another point. So 1 volt is defined as 1 joule of work is done to bring 1 coulomb of charge from one point to another point within the conductor. Within the conductor is called potential difference. So 1 volt equal to 1 joule by 1 coulomb. So here I am considering very, very important electrical potential. Next one is electrical potential. Electrical potential. Here Electrical potential is nothing but here I am considering. So this is the required field. So suppose I am taking the required field. So this is the charge. So charge is at infinity. So Q is a charge. Charge is at infinity. Okay. So charge is at infinity. We are doing some work. To bring unit positive charge. We are doing some work to bring unit positive charge. We are doing some work to bring unit positive charge from one point to another point. Within the so like this. So we are doing some work to bring positive charge from infinity to the required field. So electrical potential is nothing but we are doing some work to bring unit positive charge from infinity to the required field is called electrical potential. Infinity to the required field is called electrical potential. Potential difference is nothing but we are doing some work to bring unit positive charge. So potential difference and electrical potential. Potential difference I am considering here. Potential difference and electrical potential. Potential difference is nothing but work done to bring unit positive charge. From one point to another point within the conductor. Is called potential difference. So work done to bring unit positive charge from infinity to the required field. Work done to bring unit positive charge from infinity to the required field is called electrical potential. Once again, potential difference is nothing but within the conductor we are doing some work to bring unit positive charge from one point to another point. Electrical potential is nothing but we are doing some work to bring unit positive charge from infinity to the required field. That is called electrical potential. I hope it is very clear to you all. So this is about potential difference. And electrical potential. I hope it is very clear to you all. So be very clear, be very specific. Within the conductor from one point to another point. That is called potential difference. Work done to bring unit positive charge from infinity to the required field is electrical potential. So very important. Simple term, easy terms, simple terms. So remember very easy terms. Within the conductor, one point to another point, that is potential difference. From infinity to the required field is called electrical potential. Clear? I hope it is very clear to you all. So next one we are going to the next one. So we'll go and discuss about Ohm's law. Okay, so next one we are going to discuss about Ohm's law. Okay, sorry for it, just a small break. So water, take to drink water. Next we are going to discuss about Ohm's law. We'll see. Ohm's law is nothing but, so very simple. The point is, so here Ohm's law. So I'm considering here, this is the resistor, switch, ammeter. Ohm's law. Ammeter. So across it, voltmeter we have to connect. Across it, we have to connect voltmeter. Voltmeter connect here. So here current is passing from here I. So positive terminal, negative terminal, positive terminal to negative terminal current is passing. I am considering here. So this is about circuit diagram. This is circuit diagram. Circuit diagram. Ohm's law is nothing but, so at a constant temperature, the potential difference at a constant temperature, the potential difference across the metallic conductor. So at a constant temperature, the potential difference across the given metallic, across the ends of the given metallic conductor is directly proportional to current flowing through it. Is directly proportional to current flowing through it. Once again, at a constant temperature, the potential difference at a constant temperature, the potential difference across the ends of the given metallic conductor, is directly proportional to current flowing through it. Is directly proportional to current flowing through it. Once again, you can see, observe. You can observe once again. So the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. Is directly proportional to current flowing through it. Once again, the potential difference across the ends of the given metallic conductor. Okay, so I'm considering this is a resistor. Across the ends of the metallic conductor. So ends of the given metallic conductor is directly proportional to whatever the current is flowing. So V is directly proportional to I. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. At a constant temperature, the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. Once again, so across the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. Okay, so V equal to IR. So R equal to V by I. R equal to V by I. R equal to V by I. So Ohm's law gives the definition of resistance. 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 Once again, here, so the potential difference across the ends of the given metallic conductor. So the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. V is directly proportional to I. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. R equal to V by I. R equal to V by I. Ohm's law gives the definition of resistance. Ohm's law gives the Ohm's law gives the definition of resistance. 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 Okay. So V is directly proportional to I, V equal to IR, R equal to V by I. So materials required. What are the materials required? Materials required. Materials required. Materials required. So I'm considering here, first one you have to take the nichrome wire. First one, 4 cells. Here you see 4 cells. So the potential difference across the ends of the given metallic conductor. The potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it at constant temperature. At constant temperature, the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. That is about Ohm's law. I hope it is very clear. Okay, right. Now materials required. First one is, so 4 cells I am taking. 4 cells. 4 cells I am considering. 4 cells. Okay. 4 cells. 4 cells. 4 cells. 4 cells of here, these are the 4 cells, 1.5 volts each, 1.5 volts each, 1.5 volts each, 1.5 volts each. So each cell consists of 1.5 volts, 1.5 volts. Okay, so each cell is potential difference is 1.5 volts each. So how many cells are required? 4 cells, 1.5 volts, 1.5 volts of each. Okay, so 1.5 volts each. Second thing. So nichrome wire of okay, so 0.5 meter length. And coming to the third one, nichrome wire. Nichrome wire is an Li of, so here is X and here is Y. Nichrome wire is an Li of nickel, chromium, manganese and iron metals. Nichrome wire is an Li of nickel, chromium, manganese and iron metals. Nichrome wire is an Li of nickel, chromium and manganese and iron metals. Nichrome wire is an Li of nickel, chromium, manganese and iron metals. Nichrome wire is an Li of nickel, chromium, manganese and iron metals. Okay, so that is an Li. So I'm considering here. So next one I am considering 4 cells and a nichrome wire. 4 cells and nichrome wire. Next one, ammeter. Ammeter I am taking. Ammeter. Fourth one is voltmeter. And fifth one, so ammeter, voltmeter. Next, switch I am taking. Switch I am considering. Okay, this is the switch I am taking. Okay, switch I am taking. Next one, sixth one, connecting wires. 4 cells, nichrome wire, ammeter, voltmeter, switch, connecting wires. Next one, connecting wires. So these are the materials required. Once again, materials required. What are the materials required? One is 4 cells. 4 cells are 1.5 volts each. 4 cells are 1.5 volts each. Nichrome wire is an Li of nickel, chromium, manganese and iron metals. So ammeter, voltmeter, switch and connecting wires. Connecting wires. I hope it is very clear to you all. Next one, procedure. What is the procedure to do that? So procedure. Okay, so procedure. So procedure if you are considering, procedure. So first you have to connect one cell. Connect one cell and note down the reading of. Okay. First you have to connect one cell and note down the reading of ammeter and voltmeter. First connect one cell and note down the reading. See here you can see first you have to connect one cell and note down the reading of ammeter and voltmeter and mention in the tabular form, and connect two cells and connect two more cells you have to connect and note down the reading of ammeter and voltmeter. Okay, so you have to read, you have to identify the reading of ammeter and voltmeter. Next, connect to two cells. Second one, connect to two cells, and repeat the process for 3 and 4. Repeat the process for repeat the process for 3 and 4. Repeat the process for 3 and 4. 3 and 4. Okay. So repeat the process for 3 and 4. Once again, first connect one cell and note down the reading of ammeter and voltmeter, and next connect two cells. So I am considering here. First connect one cell and note down the reading of ammeter and voltmeter. Connect to two cells and note down the reading of ammeter and voltmeter. Repeat the process for 3 and 4. Repeat the process for 3 and 4, and mention the readings in the tabular form. Mention the readings in the tabular form given below. Mention the readings in the tabular form given below. So like this we can understand. So this is about Ohm's law. Once again we will discuss. So Ohm's law is nothing but the potential difference across the ends of the metallic conductor. The potential difference across the ends of the metallic conductor. The potential difference across the ends of the metallic conductor is directly proportional to current flowing through it. Is directly proportional to current flowing through at constant temperature. At a constant temperature is very, very important. At a constant temperature, the potential difference across the ends of the metallic conductor is directly proportional to current flowing through it. And also physical conditions also will be same. Physical conditions also. Okay, so V is directly proportional to I, V equal to IR. V is directly proportional to I, V equal to IR. V equal to IR. Okay, so Ohm's law gives the definition of resistance. Ohm's law gives the definition of resistance. Materials required. What are the materials required? First, 4 cells of 1.5 volts each. 4 cells of 1.1, 1, 2, 3, 4. 4 cells I am taking. So 4 cells of 1.5 volts each. Each cell potential difference is 1.5 volts. And nichrome wire is an alloy of nickel, chromium, manganese, and iron metals. Nichrome wire is an alloy of nickel, chromium, manganese, and iron metals. Next one, ammeter, voltmeter, voltmeter, switch I am taking, and connecting wires. Once again, materials required. What are the materials required? So 4 cells, 1.5 volts each, nichrome wire, ammeter, voltmeter, switch, and connecting wire. So these are the materials required. Okay, proceed. What is the procedure? So procedure is, first you have to connect one cell. And note down the reading of ammeter and voltmeter. First you have to connect one cell and note down the reading of ammeter and voltmeter. Connect to two cells. Again, note down the reading of ammeter and voltmeter. and repeat the process for 3 and 4, repeat the process for 3 and 4, repeat the process for 3 and 4, repeat the process for 3 and 4. Okay, and so mention the values in the tabular form given below. So you have to mention the values in the tabular form. Now if you draw the graph for vi, okay, so vi, if you are taking vi, is a straight line for ohmic conductors. vi is a straight line for ohmic conductors. For non-ohmic conductors, the graph is curve. So VI graph is straight line for ohmic conductors. VI graph is straight line for ohmic conductors. VI graph is curve for non-ohmic conductors. Non-ohmic conductors. So what are the ohmic conductors? Ohmic conductors are nothing but the substances which obey Ohm's law. The substances which obey Ohm's law, those are called ohmic conductors. The substances which does not obey, those are called non-ohmic conductors. The substances which obey Ohm's law, those are called ohmic conductors. The substances which does not obey Ohm's law, those are called non-ohmic conductors. Once again, the substances which obey Ohm's law, those are called ohmic conductors. The substances which does not obey Ohm's law, those are called non-ohmic conductors. For Ohm's law, the graph is VI graph is linear, that is very much straight line. So starting from origin. Okay. So for non-ohmic conductors, the graph is curve. So okay. So this is about Ohm's law. Next one, resistance. So actually, in the diagram I explained about resistor, right? So that I will explain once again. Here resistance we got right, R equal to V by. So this one R equal to V by. Okay. So what is that resistance? So we'll discuss now. So resistance is the phenomena of opposing the electric current in the circuit. Resistance is the phenomena of sorry. Resistance. So R is directly proportional to length of the conductor. R is inversely proportional to area of the conductor. R is directly proportional to L. R is inversely proportional to area of the conductor. R equal to L by A. R equal to rho into L by A. R equal to rho into L by A. R equal to rho into L by A. Okay. So I am considering here. Now rho equal to RA by L. Rho equal to RA by L. Here R is a resistance. So I am considering the resistance. R is a resistance. Okay, chalo. Here I am considering R is a resistance. Rho is the resistivity. Okay, so R is the resistance, rho is the resistivity, rho is the resistivity. Okay, done. Now you are considering here SI unit of resistance is very important. SI unit of resistivity. Okay, so I'm considering here. You can check here. Okay, yes. Here rho equal to SI unit of resistance is ohm. SI unit of resistance is ohm. SI unit of area is meter square. SI unit of area is meter square. Okay, so meter square I'm taking. Meter square. So SI unit of length is meter. So now you can observe. So this meter get cancelled. So meter get cancelled. Then we will get value is ohm meter. Rho equal to ohm meter. Rho equal to ohm meter. Very important. Very important. Ohm meter. Okay, understood. Understood. I hope it is very clear to all. Once again, you can check. So resistance is directly proportional to length of the conductor. Resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the conductor. Resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the conductor. R equal to L. R is directly proportional to L by A. R equal to rho into L by A. Rho equal to RA by rho equal to RA by L. So SI unit of resistance is ohm. SI unit of area is meter square. Length also meter. So now if you cancel it, so meter get cancelled, then you will get resistivity is ohm meter. Resistivity is ohm meter. I hope it is very clear to you all. Okay. So next one we'll discuss about one more. One more you are considering. So that is very important question. This they will ask for a explanation. They from here to here they will ask for 2 marks. They will ask for 2 marks. Very important. And this one especially only this one they will ask for 1 mark. Only resistivity, SI unit of resistivity they will ask. And this derivation they will ask for 2 marks. Okay. So and anyway these factors they will ask. Now we'll discuss about difference between resistance and resistivity. Difference between resistance and resistivity we'll discuss. Difference between resistance and resistivity we'll discuss now. You can check here. Yeah, of course. It happens. Okay, done. Now we'll discuss about resistance and resistivity differences. Resistance and resistivity. Resistance. Resistance and resistivity. So first one. First point is resistance. So resistance depends on R equal to rho into L by A. So here first one is rho equal to RA by L. Second one, resistance is SI unit of resistance is ohm. Here SI unit of resistivity is ohm meter. Ohm meter. So here third one. So SI unit of resistance symbol if you are taking this is symbol. Symbol I am considering here. So this also symbol only. This also symbol. Okay. So I am taking third one. So resistivity. So ohm meter symbol. Okay, next I am considering one more. So fourth one. So resistance depends on length of the conductor. Resistance depends on length of the conductor. Resistance depends on length and area. So here fourth one, resistivity does not depend on length and area, because it depends on. So here resistivity does not depend on length and area. Only resistance depends on length and area. Now fifth one. So resistance depends on temperature, and here resistivity depends on temperature, and here sixth one, it also depends on material of the conductor. Material, it also material. So very very important points. These are very very important points. Resistance, once again you can check here. You can check. So resistance depends on. Okay, chalo. So resistance is R equal to rho into L by A. So R equal to rho into L by A. R equal to rho into L by A. So SI unit of resistance is ohm symbol. So resistance depends on length and area. Resistance depends on length and area. So resistance depends on temperature. Resistance depends on material. Whereas resistivity, rho equal to RA by L. Rho equal to RA by L. Very very important. Make sure that you are learning. So SI unit of resistivity is ohm meter. SI unit of resistivity is ohm meter. SI unit symbol I am taking. So resistivity does not depend on. Resistivity does not depend on. Resistivity does not depend on length and area. Resistivity does not depend on length and area. Resistivity depends on temperature, and resistivity depends on temperature, and also resistivity depends on material of the conductor. Right? So I hope it is very clear to you all. Okay. So that's enough. So that is about resistance and resistivity. Okay. So now, we will go to the one more chapter. We'll discuss about one more chapter, that is resistors are connected in series combination. Resistors are connected in parallel combination. We'll discuss. Resistors are connected in series and resistors are connected in parallel combination. We'll discuss. Okay. So let's get into the topic. Now, resistors are connected in series. Resistors are connected in parallel. Resistors are connected in series. Resistors are connected in parallel. So next topic is, so we'll see how it is. Series combination. So resistors are connected in series combination. So we'll discuss now. So how you are connecting? How you are connecting resistors are in series means. So if you are taking all resistors, so I'm considering here 1, 2, 3. So I'm taking this ammeter. Current is passing. Here is the battery. So switch. Positive terminal, negative terminal, current is passing. Here V1, V2, V3. Okay, so now across R1 is V1, across R2 is across R3 is V3. So across V1 across R1 is V1, across R2 is V3, across R3 is V3. So current is passing like this. So here current. Now this also current only. So throughout the circuit, throughout the circuit, current is same. Throughout the circuit, current is same. Throughout the circuit, current is same. Yes or no? So then we can take from Ohm's law. From Ohm's law, V equal to IR. From Ohm's law, V equal to IR. So from Ohm's law, V equal to IR. Current is passing. So I'm considering like this. Okay, done. As I said, throughout the path, current is same. Throughout the path, current is same. As I said, throughout the path, current is same. Yes or no? Yes. From Ohm's law, V equal to IR. V equal to IR, right? So Vs equal to potential difference. Vs equal to V1 plus V2 plus V3. So why potential difference in a circuit, overall circuit is potential difference in overall circuit is equal to, so potential difference across V1, potential difference across V1, potential difference across V2, potential difference across V3. So Vs equal to V1 plus V2 plus V3. Vs equal to V1 plus V2 plus V3. So Vs equal to Vs equal to V1 plus V2 plus V3. So Vs I am taking. So here current is same. Is equal to I1 equal to I2 equal to I3. Okay, so there are current is entire the circuit current is same. Entire the circuit current is same. Yes or no? Entire circuit current is same. So potential difference in a circuit in a series circuit in a series combination Vs equal to V1 plus V2 plus V3. Vs equal to V1 plus V2 plus V3, right? So that's why I'm considering here Vs equal to, so Vs equal to, we can also take IRS, Vs equal to IRS, why are taking IRS? Vs equal to Vs equal to Vs equal to IRS, right? So from that we can take IRS equal to IR1 plus IR2 plus IR3. Shall I take V common? So anyway, V is common only. So I'm taking V common. So if I take V common, so IRS equal to, I am taking common. The remaining value R1 plus R2 plus R3. R3. So I get cancelled. Then RS equal to R1 plus R2 plus R3. So this is the value. If in a series combination, if all resistors are connected, simply we have to add all the resistance. You have to add all the resistance. You have to add all the resistance. That's enough. In a series combination, in a series combination, in a series combination, in a series combination, if resistors are connected, you must add all the resistance. Then you will get the value of total resistance. If n number of resistors are connected in series combination, if n number of resistors are connected in series combination, if n number of resistors are connected in series combination, what happens? If n number of resistors are connected in series combination, what happens? We'll discuss. N number of resistors. N number of resistors. So then Rs equal to Nr. Rs equal to Nr. So Rs equal to Nr. If n number of resistors are connected in series combination, if n number of resistors are connected in series combination, Rs equal to Nr. Rs equal to Nr. If n number of resistors are connected in series combination, Rs equal to Nr. Okay, so clear? Is it clear? So I hope it is very clear. Just check once. So in a series combination R1, R2, R3, so we connected in such a way that so entire the circuit current is same. Entire the circuit current is same. Okay. So the IS equal to I1 equal to I2 equal to I3 equal to I only. I only we can consider. So we can take I. We can take I. So anyway, everything is I'm taking I. Everything I'm taking I. Everything I'm taking I. Okay. So IS equal to I1 equal to I2 equal to I3. Okay. So I1 equal to I2 equal to I3 equal to IRS equal to IRS equal to I. So that's why. So VS equal to potential difference is different. So different resistors we are considering, right? So if you are taking different resistance, potential difference also different only, right? Potential difference is different. That's why. So R1, R2, R3 across R1, V1 across R2, V2 across R3, V3 across R1, V1 across R2, V2 across R3, V3. So that's why I'm taking here V equal to IRS. Vs equal to V1 plus V2 plus V3. Vs equal to V1 plus V2 plus V3. So Vs equal to IRS. That's and so on. V1 equal to IR1, V2 equal to IR2, V3 equal to IR3, and so like that we can write. So that's why IRS equal to IR1 plus IR2 plus IR3. So IRS equal to I we are taking common. I we are taking common. So if you are taking I common, RS R1 plus R2 plus R3. I get cancelled. II can cancel. So both II can cancel. So if you are cancelling II, then the remaining value RS equal to R1 plus R2 plus R3. 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 So RS equal to NR. If n number of resistors are connected in series combination, if n number of resistors are connected in series combination, if you want to calculate the total resistance, if n number of resistors are connected in series combination, if you want to find out the total resistance in a series combination, Rs equal to Rs equal to Rs equal to NR. Rs equal to NR. Very, 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 very important. Okay, so shall we go to the next one? So I'm going to the next one. That is about the resistors are connected in parallel combination. Resistors are connected in parallel combination. If resistors are connected in parallel combination, if resistors are connected in parallel combination, how we have to take the formula, we can see now. Resistors are connected in parallel combination. So if resistors are connected in parallel combination, so how it will be, we can see now. We can see. So if resistors are like this, so I'm taking here. So ammeter I'm taking here. I'm considering here battery. So switch. So current is passing. Parallel combination. This is the R1, R2, R3. Across R1, R2, R3, we are connecting potential difference. Across R1, R2, R3, we are connecting potential difference. Across R1, R2, R3. Okay. So R1, R2, R3. So when the current is passing here, that current will be divided I1, I2, I3. So across R1, I1, across R2, I2, across R3, I3. Once again, across, across, across R1, I1, across. So if the current is passing, suppose if the current is passing, so through R1, I1, through R2, I2, through R3, I3. Okay. So current is passing. Current is splitting into three parts according to the resistors. According to the resistors, the current is splitting into parts. Right. Now you are considering V equal to IR from Ohm's law. From Ohm's law, V equal to IR. From Ohm's law, V equal to IR. V equal to IR. I equal. So we are taking I equal to V by R. V by R. Because current is different in different resistors. So through R1, R2, R3, through R1, R2, R3, through R1, R2, R3, current is different. Current is different. Okay, R1, I1, R2, I2, R3, I3, R1, R1, I1, R2, I2, R3, I3. So current is different through different resistors. Yes or no? Now IP, if you are taking in this case VP equal to V1 equal to V2 equal to V3 equal to V. Clear? Yes or no? So Vp equal to V1 equal to V2 equal to V3 equal to V. Yes. Now, so we know that. So Ip equal to, so current in parallel combination I1 plus I2 plus I3. So Ip equal to I1 plus I2 plus I3. Yes or no? I1. So IP, overall current in parallel combination. Overall current in parallel combination. IP equal to I1 plus I2 plus I3. IP equal to I1 plus I2 plus I3. So we are taking V by RP equal to V by R1 plus V by R2 plus V by R3. Okay. So VBK we can take common 1 by RP equal to, so we are taking common 1 by R1 plus 1 by R2 plus 1 by R3. So VV can cancel. VV can cancel it. So I'm cancelling VV. So potential here. So the remaining value is so 1 by RP equal to 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is the value. Here once again, so all resistors are connected in parallel combination. All resistors are connected in parallel combination. So across, so through R1, I1, through R2, I2, through R3, I3. Okay, so current, whatever the current is passing from the battery, it's split into three parts. It's split into three parts. I1, I2, I3. I1, I2, I3. So the overall current in the parallel combination is, so IP equal to IP equal to I1 plus I2 plus I3. IP equal to I1 plus I2 plus I3. So here I'm considering from Ohm's law V equal to IR, I equal to V by I. So V by RP plus V by RP equal to V by R1 plus V by R2 plus V by R3. So here in the place of IP, we can take V by R. In the place of I, we can take V by R. So in the place of I, we can take V by R. Same that V by RP equal to V by R1 plus V by R2 plus V by R3. So here overall V. Here also V I am taking common. 1 by RP equal to, so we are taking common, we get cancelled. 1 by R1 plus 1 by R2 plus 1 by R3. 1 by R1 plus 1 by R2 plus 1 by R3. Is it clear? So I hope it is very clear to all. So that's enough. The resistors are connected in parallel combination. 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. If n number of resistors, are connected in parallel combination, if n number of resistors are connected in parallel combination, if n number of resistors are connected in parallel combination, if n number of resistors are connected in parallel combination, so if n number of resistors are in parallel combination, so 1 by Rp equal to so n by R. So Rp equal to R by N. Rp equal to R by N. I hope it is very clear to all. So check once. If n number of resistors are connected, if n number of resistors are connected, in a parallel combination, if n number of resistors are connected in parallel combination, okay, so 1 by Rp equal to N by R, Rp equal to R by N. Reciprocal we are taking. I hope it is very clear to all. So do you have any doubts in this? So we'll go to the next one. We'll go to heating effect of electric current. Shall we? So let's get into the topic. Next topic. So resistors are connected in parallel combination. Resistors are okay. So normally, if you are considering now, if you are considering now, okay, done. So now let's get into the topic. So we know potential difference is equal to heating effect of electric current. Next topic, heating effect of heating effect of electric current. So what is heating effect of electric current? By passing the current, heat will be produced. The source of energy continuously gets dissipated entirely in the form of heat. The source of energy continuously gets dissipated. The source of energy continuously gets dissipated entirely in the form of heat. The source of energy, the source of energy the source of energy continuously gets dissipated entirely in the form of heat is called heating effect of electric current. So V equal to, we know potential difference V equal to W by Q. So V equal to W by Q. So W equal to V into Q. W equal to work done equal to V equal to V equal to W by Q, W equal to V into Q. So power is nothing but rate of doing work. Electrical power is nothing but rate of doing work. Electrical power is nothing but rate of doing work. So P equal to W by T, P equal to W by T. Now, so W equal to what? What is the W value? VQ. W equal to VQ by T. W equal to VQ by T. W equal to VQ by T. Understood? So V is nothing but V into Q by T is what? Q by T is current. Q by T is the current. Yes or no? Q by T is the current. So Q by T I am taking current I. So I am considering Q by T is current. So from here V into I, V into I. So P equal to V into I. P equal to V into I. So now, what are the energies given to the conductor? What are the energies given to the conductor? Whatever the energy is given to the conductor, so E equal to P into T. So what are the energy that will be converting in the form of heat? So in the form of heat. So P into T. So here P equal to what? VI. So H equal to VI into T. Normally V value equal to I into V equal to IR from Ohm's law. V equal to IR. So H equal to IR into I into T. So then you will get I square RT. I square RT. So heating effect of electric current is nothing but so heating effect of electric current. Heat produced in the conductor. Heat produced in the conductor is directly proportional to heat produced in the conductor. Now we can observe heat produced in the conductor is directly proportional to current flowing through it. Heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to square of current. Square of current. So you can see here, heat produced in the conductor is directly proportional to square of current. Heat is directly proportional to resistance. Heat is directly proportional to time. Okay. So now you can consider. So V equal to W by Q. So potential difference is nothing but work done to bring unit positive charge from one point to another point. Work done to bring unit positive charge from one point to another point. Work done to bring unit positive charge from one point to another point. That is potential difference. So W equal to VQ. So W equal to VQ. So we know power equal to rate of doing work. Rate of doing work. P equal to W by T. So W we know V into Q. VQ into VQ by T. So V into Q by T, that is nothing but VI. P equal to VI. P equal to VI I am considering. So here, so P equal to VI. Now energy produced, that is nothing but power into T. So H equal to P into whatever the energy is given to the conductor, the total will be converted in the form of heat. So H equal to P into T, H equal to VI into T, V equal to IR. From Ohm's law, potential difference equal to potential difference is nothing but IR. So that is nothing but V equal to IR. So H equal to IR into I into T. So I square RT. So heat produced in the conductor, heat produced in the conductor, heat produced in the conductor, heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time, directly proportional to time. So this is about heating effect of electric current. Heating effect of electric current is also known as Joule's law of heating. Heating effect of electric current is also known as Joule's law of heating. Heating effect of electric current is also known as Joule's law of heating. Heating effect of electric current is also known as Joule's law of heating. Heating effect of electric current is also known as Joule's law of heating. Heat produced in the conductor. Heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time. Is directly proportional to time. Directly proportional to time. Clear? Yes. Now, so that's enough. That is about maximum points we discussed. Short circuit is nothing but the direct contact of liver and neutral wire takes place, then heavy amount of current will be drawn from the mains. So short circuit is nothing but short circuit, as I said, the direct contact of liver and neutral wire takes place, heavy amount of current will be drawn from the mains. That is called short circuit. Overloading is nothing but high voltage appliances on at a time. So heavy amount of current will be drawn from the mains. So it leads to the short circuiting. So next one, live wire is the live wire, at also called phase wire, live wire or phase wire. So that is a positive terminal. So we'll discuss now once again. So live wire, neutral wire, so earth wire. So we'll see. So now we are going to one more. That is nothing but that is that is that is that is that is that is so we are discussing about live wire. Live wire is also called phase wire. Live wire, live wire. That is also positive. Okay, and potential difference is 220 volts. So coming to the neutral wire. Neutral wire is earth wire. Sorry, neutral wire is a negative terminal. Negative term. Negative terminal. Negative terminal. Sorry, negative terminal. Potential is. So negative terminal. Potential is 0 volts. Whereas earth wire, neutral wire is so zero potential. Okay, so earth wire. So once again, live wire is also called phase wire. So live wire is a positive terminal, and also it is a red insulation, red color, red in color live wire. Neutral wire is black color, neutral wire is black color, and earth wire is green color. Okay, so observe carefully. Very important here. Very important. So live wire is positive terminal, 220 potential difference. Whereas neutral wire is negative terminal. So black in color. Earth wire is green color. So here live wire potential difference is 220. Live wire potential difference 220. Neutral wire is potential difference 0. Earth wire potential is 0 volts. Okay. Live wire potential difference 220. Neutral wire potential difference 0. Earth wire potential difference is 0. Okay. But if they ask in the exam, the potential difference between live wire and neutral wire is the potential difference between live wire, that is nothing but live wire and neutral wire is 220. That is the first one. Coming to the, so sometimes they will ask about neutral wire and earth wire. Neutral and earth wire is zero potential. And coming to the third one, so they will ask about potential difference between earth wire and live wire and earth wire. Live wire and earth wire also live wire and earth wire 220. Only difference between neutral wire and earth wire is 0. Live wire and neutral wire is 220. Live wire and earth wire is 220. So only between neutral and earth wire is 0. So very, very important. So these questions they will ask in exam. So make sure that you are learning these points. Okay. So this is about electric current. So I hope it is very clear to you all. Right. Next one. So next we will discuss about problems only. We'll discuss, right? So if you like this video, please do like, share and subscribe to Student Brand. If you like this video, please do like, share and subscribe to Student Brand. If you like the explanation, if you like the content, you can share to your friends. Ask your friends to join to the class. Okay. So this is your sir from Student Brand. So finally, I'll sing one song for you. Not a song. It's related to subject only. Whatever I sang in the starting. Myopia, myopia, myopia. Myopia, myopia, myopia. Near distance we can see far distance we can't see myopia, 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 myopia. For that correction we are using, bro. What, bro? For that correction we are using concave lens, concave lens, concave lens, concave lens. Hypermetropia, 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 hypermetropia. Far distance we can see, near distance we can see. Hypermetropia, hypermetropia. Convex lens, convex lens. For that correction, we are using convex lens, convex lens, convex lens. Hypermetropia, convex lens. New Cartesian sign convention, new Cartesian sign convention. All distance measured from the pole, distance are positive along the instant ray. Distance are negative opposite to instant ray. Distance are positive above the principal axis. Distance are negative below the principal axis. New Cartesian sign convention, new Cartesian Sign convention, all distance measured from the pole. Distance are positive along the incident rays. Distance are negative opposite to incident rays. Distance are positive above the principal axis. Distance are negative below the principal axis. So thank you so much for joining and attending and listening my class. Thank you so much. Please do like, share, and subscribe to Student the Brand. If you like this content, this is your Siva sir from Student the Brand. So signing off. Namaste. Thank you.